Hello again, it's Scott Arthur here. I'm the course leader for D21UD. Welcome to class 3A. So in the last two classes we looked at the characteristics of surface and combined pipe networks, and to a lesser extent we looked at sustainable urban drainage systems. We'll come back to them later in the course. As part of the classes last week, we looked at how we estimate foul flows coming into the pipe network. In this week's class, in 3A, we're going to look at how we estimate the amount of rainfall which falls in a catchment, particularly in the UK. And in the next class, 3B, we'll look at how we estimate how much of that rainfall converts to runoff, which is almost as important as being able to estimate the rainfall as being able to estimate how much of it converts to runoff and enters the system. It has to be managed. So you remember in earlier classes we spoke about how we can't design our pipe network to accommodate every single storm event, because if we did that, the construction costs would be huge and the maintenance costs would also be huge as well. So by and large, what we try to do is balance the cost of the system, the whole life cost, against the risk of failure. I'll clarify this in the next slide, but by and large, for small, simple pipe networks, so for new developments, etc., we tend to focus on design for surcharging. So that means that the water doesn't go past the top of the pipe diameter. And then we check for flooding. Flooding's where the water goes beyond the top of the pipe diameter, up the manhole shaft, and out onto the surface. So basically we're designing for surcharging, but then we check for flooding. There's exceptions to that. So you could see that in the table below, that this approach means that in low risk areas, so in a rural area, surcharging might be designed for 1 in 1 year. So typically this pipe surcharge is once per year. Residential areas, they've got double the level of protection, 1 in 2 years, which is still not huge. But then once you get into higher risk areas, 1 in 10. It's important to remember this is different from the risk of flooding. This is about the risk of surcharging. But stepping back, we could set a number of design criteria. So we could look at expected rainfall frequency at which there would be no surcharge, and that's really what the table in the previous slide was about. Expected rainfall frequency at which a specified amount of surcharge occurs. I think it'd be quite unusual to use that design approach, to be honest. The expected rainfall frequency of which sewer or surface water flooding occurs. It's not very clearly worded, I'll have to change that. So that's really what residents are concerned about. They don't really care about how often the pipe surcharges below the ground. They're interested in what is the risk of flooding in this area. The impact of the flows from surface water outfalls. So that could be either discharge from your separate system into the river, or in addition to what's in the bullet point there, the CSO into the river. How often is that going to happen? And at what volumes, etc. The impact of flows on the operation of wastewater treatment plants. So in Scotland, the guidance reads like this. So the surface water system shall be designed and constructed so that flooding does not occur in any part of the site in a 1 in 30 year period, with a 1 in 200 year overall minimum flood resilience assessment check as may be required. So what that means is the network's designed for 1 in 30 years, so there's no flooding at the 1 in 30 year event. Then it's checked to see what happens during the 1 in 200 year event. So for example, if you have a network which is fine at 1 in 30, but then for the 1 in 200 year event it floods, say, a park, people might not be very concerned about that. But if at the 1 in 200 year event it floods a GP surgery, an ambulance station, an accident and emergency unit, a fire station, an electrical substation, generally that would be perceived to be a bad thing, and additional investment or a change to the design would be required to stop that from happening. Bullet point 2, surface water drainage shall be designed for runoff from roads and subject to agreement from Scottish Water, roads including verges and other handstanding areas. For these areas, an impermeability, so it's runoff coefficient for 100% will be assumed. So that's saying that Scottish Water will accept runoff from roofs, so that's because that's their responsibility, is to drain properties, and subject to agreement, Scottish Water, roads and verges. And this is because in Scotland local authorities are responsible for draining roads, but normally through agreement with Scottish Water, the Scottish Water will take those flows. But it's saying it expects the runoff coefficient for the roads and verges is to be 100%. An additional increase in the paved surface area of 10% shall be assumed for all areas to allow for future urban expansion. So it's talking about extensions to the property there and also additional paved areas. And this is about how, sure, it's not just in Scotland it happens, how people quite often will pave over their garden to provide an extra car parking space. An allowance for climate change of an additional 30% is placed on the rainfall. So you estimate your rainfall based on 100% runoff rate from your roads and verges, etc. And then on top of that you add 30%, and that's to ensure that, up to the 2080 scenario, there's no flooding in new developments as a result of climate change. So this talks about the design for surcharge but check for flooding approach, and re-emphasises the point I make that actually customers or residents are more concerned about avoiding flooding rather than anything. So that's for small, simple developments. The reality is that design approach, which can be based on hand calculations, which we'll cover in class 4, I think it is, whilst it's perfectly adequate, and the vast majority of pipes in the UK have probably been designed in that way, or methods approaching it, it doesn't really take into account the dynamic nature of sewer flows, or really doesn't fully utilise the storage which is available in systems. So it tends to be that for bigger networks, or if you're checking the performance of a large existing network, you would tend to use what's called their sewer flow simulation models to do that. So whilst a small development can be designed using the design for surcharge, check for flooding approach, hand calculations on your own spreadsheet or whatever, when it comes to looking at, well, how does this development connect with the existing network, and how does the network as a whole perform, and there are a number of different scenarios, you would use sewer flow modelling software to do that, absolutely. And to do things like estimate CSO spills, etc., you really need to use computer models to do that accurately. So when assessing the levels of risk involved with any given level of protection, it's important that all those involved understand what is meant by a return period. So I've kind of used this phrase already in the lectures over the past few weeks, but it's really about probabilities. An n-year return period simply conveys the average likelihood of the event occurring or being exceeded within n years. So if I talk about a 30-year return period flood protection, what that means is that there's a likelihood, the likelihood is that event will occur or be exceeded over a 30-year period. So it's about probabilities really. So of course what that means is that does not mean it's going to flood every 30 years, and it does not mean it is definitely going to flood over a 30-year period. It just means that on average we would expect that event to occur or be exceeded. It's perfectly possible that you get a 1 in 30 year event twice in a year. It'd be really unusual, but it is possible. So conveying this to the public sometimes can be problematic, and it's recognised that when people talk about return periods, quite often members of the public and others view it as a prediction, so it's going to flood once every 30 years. It might be their perception, rather than actually what it means is it's a probability. So there was a move a few years ago to actually talk in terms of probabilities to people, because the argument was that people understood horse betting odds and national lottery chances of winning better than they did understand storm return periods. But that move seems to have dissipated a little bit, but quite often in government documents you'll see them talking about flood return periods, and alongside that in brackets talk about the probability of a flood occurring. So this is an example from the FEH. So return periods should be viewed as probabilities rather than long-term predictions. So there is a 0.0005 probability that a 2,000 year rainfall will be exceeded next year. Inevitably, there will be periods when there will be clusters of extreme rainfall events. For example, in Northmoor near Bridgewater in Devon, a one-day rainfall event of 150 millimetres in 1968 was followed a year later by a total of 92 millimetres on 28th July 1969, just after I was born. The FEH assessed rainfall return periods for these events were 475 years and 160 years. So that means you had two really unusual events, reasonably close together over just over a 1 year period, and that is quite unusual, but it's entirely possible. So once a storm return period has been selected, it's possible to calculate the probability of the event being exceeded in any 1 year, and that's using the equation here. If we know the design life of a development, the drainage system is serving, the probability of flooding during that time might be estimated using the equation at the bottom there. So this might be useful if you've got, say, you're building a supermarket and you think the supermarket design life might be, I don't know, 30 years or 50 years. You can tell the client, well, actually, what is the probability of it flooding during that time based on the design that you've adopted, etc. So let's think about how we estimate rainfall in the UK. So in the UK we're lucky because we're a so-called maritime nation or seafaring nation. I'm talking, historically. We did collect quite a lot of rainfall data over quite a long time, and what this means is there's a relatively good understanding of the types of rainfall the UK experiences. Obviously, some of the data, which was quite a long time ago, might not be accurate, and it might be in terms of, total depths of rainfall over sort of longer periods of time, rather than a second by second rainfall we can get these days. And also you've got to think about climate change, about how climate's changing a little. So perhaps that older rainfall data doesn't represent the kind of weather we're getting now. We can debate that. But the basic point is that the massive rainfall data we have in the UK is actually a really useful asset when it comes to us looking at that data and using that to try to understand, well, what is a 1 in 30 year storm event like, and what kind of impact would it have. So the first step in quantifying surface water inputs to a system is to determine the rate at which rain falls on the catchment. So that's the intensity, millimetres per hour normally. Ideally, sewerage systems should be designed using real rainfall data. To make analysis more meaningful, the data should be related to two other variables. So you can't just talk about intensity. You have to think about the duration of the rainfall event, so that's the length of it, and also the frequency, so that's the return period of that rainfall event. So using the real rainfall data, you need quite a lot of it to do this. You can produce what is called an IDF plot, and that stands for intensity, duration, frequency. And so this IDF plot here is for a location in the UK. Rainfall is spatially variable, so you have to have rainfall for your location, not some other location. And so what you have here on this chart is the curves, IDF curves for the 1, 2, 5 and 10-year return period event. Now, this illustrates something quite useful or quite interesting about rainfall that often people don't really think about too much, but it does make sense. So if we're looking at a 10-year event, so the top curve, if we're looking at that top curve there and we're looking at let's look at the 2-hour duration 10-year event. So that tells us that the average intensity is, somewhere between 15 and 20 millimeters per hour, and it's going to remain like that for 2 hours. But if we look at a longer duration event, so say the 10-hour event, not very good to run straight lines on this, you can see that the duration is less than half that, and that's the message here. And it tends to be that if you've got storms of equal likelihood of occurring, it tends to be that the shorter events are statistically tend to be higher intensity than the longer duration events. Okay, so long duration events tend to be low intensity but high volume, because if you look at the area under the curve, it's basically the volume of the rainfall. So shorter duration events, high intensity, lower volume. Long duration events, lower intensity but higher volume. And this, we'll cover this next week when we look at pipe design. Sorry, class 4, I think it is. And so this puts a stress on the design, because one thing that causes flooding, of course, is high intensity rainfall, just the sheer amount of rainfall landing on a catchment over a given time period. But the other issue is also the volume as well, especially when it comes to storage, etc. So for most systems, and we'll come on to this in a couple of weeks' time, so I don't want to spoil it for you. Most systems have all systems have a worst case scenario storm of a given return period. There's a duration which is the worst case scenario in balance between intensity and volume. It tends to be that smaller catchments, their worst case scenario storm is smaller, and bigger catchments is longer. So the alternative to using IDF plots is DDF plots. It's really just a different way of plotting the same data. These curves are for a location next to the Edinburgh campus of Heriot University, Sighthill Industrial Estate. The red dots are actual rainfall events which were recorded over, I think, a year or so period. And what you see is what you expect. The vast majority of those dots have return periods of less than 2 years, because most of them will just be quite routine, mundane rainfall events. The two rainfall events aren't really high. I mean, these two events here, as far as the data is concerned, these are really unusual events, quite high return period events. In fact, there are anomalies to do how the data was collected, because the collected using what's called a tipping bucket rain gauge, which looks a bit like this with so that angled thing at the bottom there, that's a tipping bucket. You have to use your imagination. So what happens is rainfall falls into this. It collects in the conical section it drips through onto a thing like a seesaw with a bucket at each end, and when the bucket fills at one end, it then tips, and each time it tips back and forward. So what happened for these 2 data points is that it snowed, so the cone section filled up with snow. So there was so although it snowed, there was precipitation. The bucket didn't tip. Then it rained, so quite quickly all the rain melted the snow, and it all flushed through quite quickly. And that happened twice over this winter, so we had these 2 quite unusual events. The only genuinely rare event was this one here, which we were quite lucky to catch. So rainfall is spatially variable. What that means is there's quite big variations in rainfall patterns across the UK. If you've ever been to Fort William in Scotland, it was almost certainly raining when you were there, but that rain wasn't particularly heavy. It tends just to be what we call drizzle. Because that's a typical rainfall they get there, because it's, again, spatial variability. So in Fort William, they tend to have a lot of rainy days and lots of long rainfall events, but it tends to be low intensity. If you come to Edinburgh, we have, believe it or not, quite a lot of dry days, but the rainfall events we do get tend to be higher intensity. It's a generalisation. We get I think the rainfall volume we experience in Edinburgh compared to Fort William is we get about half the rainfall they get. Now you look, there's different DDF plots here for different parts of the UK, and you can see there's quite substantial variations right across the UK. So producing IDF plots requires quite a lot of data, and it's not something that should be undertaken lightly. Where data is not readily available, it is possible to determine statistically derived IDF or DDF plots for UK locations. This goes back to the point I was making earlier about the sheer volume of rainfall data held in the UK. The following methods are available to do this. So the Flood Studies Report, the Evaluative Procedure Volume 4, this is based on the Flood Studies Report, and the Flood Estimation Handbook, which supersedes the Flood Studies Report. So statistical rainfall data for the UK urban location may be abstracted from maps associated with the evaluative procedure. So that's covered in the last slide. This method represents rainfall events using the following format, MT-D. Using this format, T is the return period and D is the event duration. So for example, a 5-year return period storm with a 15-minute duration would look like this. It's an M5 15-minute storm. Okay, so it's just a convenient way of summarising the rainfall event. The basis of this method is the determination of, so what we're going to do, sorry, I'm jumping at the deep end there. What I'm going to do is talk you through how we can use this method to estimate rainfall for just about any part of the UK. The basis of this method is determining the M5 60-minute event depth for the catchment concerned, together with the M5 60-minute M5 2D ratio. Both these data are mapped in Volume 4 of the Volume Procedure. So no matter what rainfall event you want to determine, the first step is to look at these maps which are mentioned there to get your M5 60 rainfall depth and a ratio which represents the M5 60 minute depth and the M5 2-day depth. The M5 60-minute data is used as an indication of the amount of rainfall a catchment experience, whereas R is used to reflect the rainfall type. So low R values indicates catchments which suffer from drizzle, so Fort William, and higher values indicate catchments which experience much higher intensity events. So that's like you get in the southeast of England. Using this method, it's possible to determine rainfall intensities for events of durations between 5 minutes and 48 hours. So let's talk our way through this methodology. It's not easy to do this in a slideshow, but I'll try my best. So The method is best illustrated using an example, and this example is to find the M5 24-hour event characteristics for Edinburgh. So first of all, what we have to do is read maps A1 and A2 to get the value for the M560, and it's 12 millimeters, and determine the R value for Edinburgh, and it's 0.26. So these are the A1 plots, so the figure A1, and what this is a map of the M560 depths right across Edinburgh, right across the UK, sorry. And if we zoom into this map, we can see that the M560 value for Edinburgh is around 12 millimeters. So that means for the M560 minute rainfall event, typically comes with 12 millimeters of rainfall for Edinburgh. We then determine the R value for Edinburgh, so that's the ratio of the 60-minute and 2-day rainfall events for 5-year return period. And again, we zoom in for Edinburgh and we get a value of 0.26. You can see down in the southeast it's much darker, and that's because they get much more intense events. So now we've just done this step. We've calculated the M560 and the R value for our point in Edinburgh. I should have said actually that the handout for this, the Walnut Procedure Volume 4 photocopy of the key parts is on Vision, so it probably help you if you looked at that, print it out hopefully if you can, and look at that as I go through this. I should have said that. So the next step, remember we're after the M5 24-hour, the next step is to convert our determine the rainfall depth of a storm with a 5-year return period and the required duration. So in our case, the required duration is 24 hours. This is computed using the following equation. So the M5 24, which is what we're after because 24 is the duration that we want, is Z1 times M560. Now Z1 is obtained from figures 3A and 3B in volume 4. So let's look at that. So here's figures 3A and 3B. Okay, so the duration we want is 24 hours. We know that our Z value, our duration is 24 hours. We know our R value because we got that in the previous step, and then based on that we get our Z value. So the M5 24 hour equals Z1 times M560, so that's equal to 3.1 times 12, which is 37.2. So now we have to get, now we're actually going to get the M10 24 depth, which is actually the thing we're after. Your seeking may now be determined. To do this, we must first obtain Z2 from table A2 or A1 if it's a English location. So here, so let's look at, so that's from this table here. So this is table A2. There's also an A1 for English locations because this is something that signals one of the weakest, the links, the weaknesses in the approach, because why is there different tables for Scotland and Northern Ireland and the rest of the UK? What magically happens to the physical processes which govern the amount and the frequency of rainfall could be influenced by a political line drawn on a map. Yeah, so that does tell you some of the uncertainties in the process. So based on this, so this is our target return period and this is the M5 rainfall depth we've just calculated in the last step. We have to interpolate here, so we end up with a Z2 number of 1.17. So it's 1.17 times the 37.2. So this tells us that the 1 day duration, 10-year return period rainfall depth is 43.5 millimetres. So then we can get the average intensity for that rainfall event. Okay, so it's just taking the total depth and divided by the duration. So it gives us that. Right, areal reduction factor. Right, so if our catchment's quite small and we're looking at quite an extreme event, it's relatively easy for the atmosphere, for a cloud big enough to cover the whole of that catchment, to rain on the whole catchment at the same time. But as our catchments get bigger and bigger and bigger, it's less and less likely that the storm has the size to cover the whole of that catchment in the same way at the same time. So what we do is we adjust the rainfall intensity to take into account the fact that it's harder for the atmosphere to produce those bigger events over bigger catchments, and this is called the areal reduction factor. And there's an equation for it, or you can use figure A4 in the handout. And here we go. So we've got our required duration, and we've got the area of our catchment, we've got the required duration. So it tells us the area reduction factor is just under 0.99. So that adjusts our intensity down a little bit, but not too much. So what I normally do in class here is I give one of these place names to the students in the class, and they then work through the method for themselves. So we will do that in class, but if you're studying online, please try to work through, pick one of these examples, perhaps somewhere exotic, like if you're studying online, why not you do one of the UK's finest cities, one of my favourite cities, why not do Dundee? Right, so the VAR procedure is kind of the, if you like, if we're being polite, we'll say that's the traditional way of estimating rainfall. What's changed since the turn of the century is more and more people are using the flood estimation handbook. Scottish Water, in their design standard, they pretty much expect you to use the flood estimation handbook to estimate rainfall. And this is really, it's changed quite a bit since it was first introduced, but it's based on sort of map type interface. You just enter the place name you want to find. In this case, I've picked Edinburgh, and I've actually picked a spot not that far away from where I live in Edinburgh. And based on it, you just click on the point in the map, and it will give you your DTF plots there and then. You can download this data, and you can use it. It also gives you some variables which define the shape of these curves, and you can put these variables into software and your flow modelling software, and that allows you to then the software to then sort of use that rainfall data. One thing that's worth looking at with these curves is that, so you can see they range from the 1.3 year return period event down to quite extreme rainfall events. But when you look at the curves are actually remarkably close together. So this is the 1 in 1.3 rainfall event, and if we compare that to the, I don't know, it's the 1 in 10 there, and I think that's the 1 in 100 there. So the basic point I want to make is the 1 in 100 event probability isn't 10 times higher in depth than the 1 in 10, and likewise the 1 in 3 isn't that much higher. It's only about double. So the 1 in 10 is only about double the 1 in 1.3. So you shouldn't so often quite substantial increases in the return period considered is not doesn't result in substantial extra flows, is what I'm trying to say. For most urban drainage systems, we're looking at relatively short duration events, often just a few minutes rather than hours. The previous slide, it goes way up to 250 hours, which urban drainage systems you would very seldom use, certainly for design. Just a reminder that rainfall is spatially variable, so you have to be quite careful about picking the correct location for your rainfall. So far we've just been talking about intensity. So it says, what I see here, it's arguably unrealistic to consider rainfall only as a duration, intensity and total depth. For most applications we are also interested in intensity variation with time. So the hyetograph is called, the rainfall profile over time. Designs can normally be evaluated using synthetic storms profiles. These are basically storms which have two generic forms, frontal or convective. So convective rainfall events are largely in the UK anyway associated with the summer events. It's where you have quite high levels of evaporation from the sea or from the land. What it says here, when the land warms up, it heats the air above it. This causes the air to expand and rise. As the air rises, it cools and condenses with a cooler upper atmosphere. And that happens repeatedly up in the atmosphere, and if this process continues, rain will fall as the evaporated air, as the moisture in the air condenses as it cools. Droplets and clouds then droplets form, or droplets and clouds, and then you get high intensity rainfall. And so these are the kind of rainfall events which in the UK we talk about, summer downpours, etc. They tend to be convective rainfall events. Frontal rainfalls is where you have a warmer air mass which meets a cool air mass. They come together, and that cooling effect again causes the rainfall to occur. These tend, in the UK, much more likely to be winter rainfall events. Well, it's a bit of a generalisation. These tend to be longer duration events as well. So once the area reduced intensity has been obtained, we can use standard storm profiles to generate hyeographs. And these profile shapes are normally defined based on what's called peakedness. So that's the percentage of storms which are equally or less peaked. And for summer rainfall events, we usually look at for Wallingford procedure, we usually look at the 50% summer profile. So these rainfall events have this profile. So they start off low intensity, they build up to a peak in the middle, and then you ease off. The intensity, it's symmetrical, so it could just be copied over, and they have this cumulative volume profile which you see on the chart. So there are a number of these symmetrical profiles available. So this is the symmetrical part. Obviously that would be, you would double that up to give you the whole rainfall, so that's not the rainfall shape. Once a general profile is obtained, it can then be used with the average intensity to determine the storm profile. So once you've got your average intensity, you know for this one, for example, the peak is going to be 400% of the average intensity. So based on that, you can build up your storm profile. So synthetic rainfall events, individual synthetic rainfall events, they're the basis of understanding how your network works. That's the starting point. But as I say here, synthetic rainfall events are a powerful tool. Often system deficiencies are only demonstrated when they're assessed using real rainfall events, because the synthetic profile is clinical, it's predictable, whereas when you have real rainfall events, you could have a phase in the rainfall event where it's low intensity, it rains for a long time, that uses up quite a lot of the storage in the system. The rain eases off, it may even completely stop for hours or perhaps a couple of days, and still some of that storage is used up. Then it starts to rain again, and because some of the storage has been used up, the catchment surface is already wet, so you get more runoff. it could be that a second rainfall event, which is quite similar, causes much more disruption. So real failure events is really important, and we can look at local single event data, historical time series, annual time series, and the synthetic time series. So this is the kind of scenario I was just talking about, where you could have this part of the rainfall event which doesn't really cause any flooding, but it uses up quite a lot of storage within the network. Things ease off here and then build up again, and it could be at that second peak, even though it's lower than the first one, causes so much more disruption, or so much more flooding, or so much more CSO spills. And you only find those kind of scenarios typically when you're looking at real rainfall events. Okay, and again, I think this graph here is just to make the same point, saying that this part of the storm here could result in storage being used up, and it's only this part here which may result in flooding, even though it's much lower intensity. So historic time series. So these are time series rainfall events, is where you've got quite a lot of data collected over time. It could be many years of data, say. You could put those years of data into your sewer model, run it through, and be guaranteed that within that you would find scenarios that you couldn't really have predicted that caused stress to the system. So caused your pumps to come on much more than you expected, caused more flooding than you would have expected, caused flooding in a place you wouldn't even thought flooding might occur, cause more CSO spills, because it's the randomness of the natural rainfall event which really tests the system. Yeah, so but obviously if you're putting years of data into your network, it takes a long time for the model to run that, and then some poor engineers got to look at the outputs from that and try to make sense of it as well. A simplification of your historic time series rainfall is you can get software that takes quite long durations of rainfall and then uses stats to condense some of the key characteristics that down to a much shorter block of rainfall, and you can use that to test your network. The other thing you can do is, where time series rainfall isn't available, you can generate your own. So you've got statistical data for your rainfall characteristics from either your own sources or things like the FEH. You can use that to build up a profile of rainfall frequencies and depths within your catchment. And the way this works, it's not very clear on this figure, is that what it does is, over time, so this could be 1 year, say, it places in it points where it thinks rainfall events might occur. Okay, this is Edinburgh, you would expect more than 5 over a year, but you get the point. So for each of those start points for a rainfall event, it then populates rain cells after them. And again, this is based on the stats about when these events would occur and what the scale of the rain cells, etc. Then for each of those rain cells, we can attach a depth. And then if we add all those individual depths up, that starts to give you the profile of individual storm events over time. So using that kind of process, so even though it's not real rainfall data, it's using rainfall characteristics data, hopefully from your catchment or nearby, to generate 1 year of rainfall or 10 years of rainfall that you can then put into your sewer flow model and see what kind of impacts that has on your network. Okay, so that concludes class 3A. So I hope that's given you some idea of some of the factors which drive rainfall estimation, and also some of the methods that are used. What I would say, well, a couple of things, is that the Wallen procedure method, which I showed you, hopefully if you've tried it yourself, what you'll get is actually it's quite cumbersome. and it's quite inaccurate reading these charts, and there is some uncertainty there. Although you're not using the FEH, the software, I hope what you appreciate from that perhaps it's easier to use, you're less likely to make a mistake, and the data you get from it, there's certainly more of it. Okay, so hopefully you've got that. If you're worried about the exam, what I would say is I've never put the runoff estimation in terms of using the volume for procedure volume 4 approach in the exam paper, because I think it's quite time consuming, and I don't really think it's an approach which is worth people knowing about, because it's been used for a long time and is still used to some extent, and it's good because it illustrates the nature of rainfall across the UK, but it's not an approach that's used widely now. I think the flood estimation handbook is used much more. So if you're based outside the UK, because you're an IDL student or you're a student studying on campus, I guess I should apologise, because this has been quite UK focused in terms of rainfall estimation, but I mean different countries do this in different ways, and that's largely based on the rainfall records, and in some parts of the world, unfortunately, rainfall records are very sparse, and whilst in the methods I've been showing you, I've been drawing differences between rainfall in Edinburgh and rainfall in Glasgow, which is just 50 miles apart, sorry. In other parts of the world, rainfall is borrowed from hundreds or perhaps even thousands of miles away. I'm exaggerating slightly, but the other parts of the world don't have that luxury. But I hope that if you are from outside the UK, or you do plan to work outside the UK after you've finished studying here, I hope, well, some of this might not be directly applicable, I hope it's given you some idea of kind of what the issues are, and the fact that rainfall is spatially variable. It's really important to use real rainfall data if you can, or base your approach on real rainfall data. And I think the most important thing is, although for the remainder of this course we will focus just really, certainly in the class, on single rainfall events, the importance of running multiple rainfall events through your sewer system to really test it can't really be stated strongly enough. Okay, so that concludes the class. In the next class, and we're going, now that we know how to estimate how much rain falls on a catchment, what we're going to do is try to figure out how much of that rainfall converts to runoff, because that's what the sewer really has to be sized to accommodate, not the amount of rainfall falling from the sky, because not all of it makes its way into the network, as you'll find out next time. Bye for now.